Now we're looking at exercise 8.3, and here we have a block diagram that describes an electric motor that drives a load via an elastic axis. So we have a lot of different components here. We have I, which is the current, we have Z, which is the turning rate of the motor, Y is the turning rate of the load, theta is the angle of the transmission axis, and T here is the torque from the load. And what we're going to do is to set up a state space description for this system. And as inputs, we're going to use this capital T, the torque, and I, the current, and the output will be Y. So we're going to introduce the state variables, and it's sort of hinted in this block diagram and in the exercise that we could use these quantities Y, theta, and Z as our state variables. I'd say that's also the most natural thing to do when we look at this. So let's try and do so. So we're gonna set x1, let that be equal to y. Let x2 be equal to theta and x3 be equal to z. And then what we need to do is to find the relations between these variables from this block diagram. So let us start with the first one, x1. I'm just going to flip this paper so we can have a look at the block diagram. Right, so let's start with x1 here. So then we're going to look over here. x1 and y is the same thing now. Okay, so in a block diagram we can set up the relation between these variables in the Laplace domain. So x1 of s, same thing as y of s, is equal to what? It's equal to 1 on s times, and then we have a sum. So in that sum we have capital T plus k2 times theta. And theta, that was our second state, x2. So now we have a relation between the first state and the second state. So this is 1 on s times capital T plus k2 times x2 of s. And if we multiply this expression with s, we get s times x1 of s is equal to k2 of x2 of s, I'm flipping the order of these, plus capital T. And then we just make an inverse Laplace transformation. And remember that multiplication with s in the Laplace domain corresponds to a time derivative in the time domain. So this will be x1 dot being equal to k2 times x2 plus capital T. Okay, so that's the differential equation for the state x1. Now let's do the same exercise for the state x2. And x2, remember, was the same thing as theta. So x2 of s is equal to 1 on s times the sum of what? So we had z, which is a positive one in this sum, and then minus the z of s, then minus y of s. And what is this? Well, z of s was our third state, so that's x3 of s, and y of s was our first state, x1 of s. And then we're doing exactly the same thing here as we did in the first case. So we multiply with s to give us s times x2 of s is equal to x3 of s minus x1 on s of s, and if we make an inverse transformation here, we get x2 dot time derivative of x2 is equal to x3 minus x1. Alright, then we just have one state left, and that's x3. And x3 was z, so x3 of s is equal to, again, 1 on s times this sum, so we have mi minus ma. And what is mi and ma? Well, mi here is just k1 times the current I, k1 times I, and since we're in the Laplace domain, it's capital I of s, the Laplace transform of the current, and then mi is equal to what? It's equal to k2 times theta, so it's k2 times theta of s. So we have 1 on s times k1 times I of s, then minus k2 times theta of s, but theta of s is our second state, so that's x2 of s, like that. And now we're doing exactly the same thing as before. So we'll get s times x3 of s is equal to minus k2 times x2 of s. I'm flipping the order here again, and then plus k1 times I of s. And then we go back to the time domain to get x3 dot is equal to minus k2 times x2 plus k1 times the current I. So now as we have the relations between the states, we can set up our state space model. So let's write down the vector of time derivatives of the state, so x1 dot, x2 dot, and x3 dot. And in this linear model, this will be equal to a matrix, the A matrix as we call it, times the state vector. So just a vector with these three states concatenated, so x1, x2, and x3. And then we'll have two vectors for our inputs. So first one vector that we multiply with the input capital T, and then one vector for the input I. And then we'll also have one output y, which is a row vector times the state vector x1, x2, and x3. Okay, so let us set up or fill in the components in these matrices. So we start with the A matrix, and we can start with the relationship for x1. So what did we have? So we have this relation for x1. x1 dot is equal to k2 times x2 plus t. So we have no component of x1, and we have no component of x3, but we have k2 times x2, and then we have one t component, so we will need a 1 up there, but no current, so 0 on top of this vector. And then we look at x2, for which we found that x2 dot was equal to x3, so we need a 1 at the x3 position. Stupid pen. And then it was minus x1, so we need a minus 1 on this position, and it doesn't involve x2 itself, so it's at 0 there. And then it has no additional components, so it's a 0 in both of these vector for the x2 row. And then finally we have x3, and for x3 we had minus k2 times x2, so we'll have minus k2 in this middle place in the matrix, and then we had no more states there, so it's just 0 there and 0 there. And we had no capital T, no torque, but we have one current component. So it's K1 times the current I. So we'll add a K1 in this position. And then the only thing we have left is this output vector. But we defined x1 to be equal to equal to y. So of course all we get here is a 1 there, and then 0 and 0. Then y is equal to x1. And this matrix here is what we usually call A, and this one is just a state vector, so this one is called X. And the input vector is typically called B. Here we have two of them, so we may call this one B1 and this one B2, and the output vector is called C. So the state space model can be summarized as X dot is equal to A times X plus B1 times T plus B2 times I, and then Y is equal to C times X. Okay, so this is an example of how you can go from a block diagram and set up a state space model of a system. That was exercise 8.3.